Hello. Hello. Am I audible? Hello. Am I audible?
Yes, ma'am.
Okay. Check whether the screen is visible. Is it visible?
Yes, ma'am.
Okay. So, last lecture we have started with the Boolean algebra. Have you remembered what is definition of Boolean algebra? Anybody? We said that Boolean algebra is next version of lattice. So, what is definition of Boolean algebra? So we have already seen Boolean algebra is complemented distributive bounded lattice. So in the lattice part we have seen types of lattices. In that we have seen complemented lattice, distributive lattice and bounded lattice. Okay. So complemented lattice means what? If complement exists for each and every element of lattice, then that lattice is called as complemented lattice. Distributive lattice means what? If that lattice holds distributive property, then that lattice is called as distributive lattice. And bounded lattice means if bounds are exist for that lattice, then lattice is called as bounded lattice. Again, we have seen what are the bounds of lattice. There is least element and greatest element. So least element was denoted by 0 and greatest element was denoted by 1. So this 0 and 1 are called as bounds of that lattice. So if any lattice is having complemented, distributive and bounded property, then that lattice is called as Boolean algebra. So this was the definition of Boolean algebra. Again, after that we had seen what are the properties of Boolean algebra. So we have categorized properties of Boolean algebra into 5 types. So first type, Boolean algebra as a lattice, because lattice Boolean algebra is next version of lattice. So whatever properties are satisfied by lattice, all those properties are satisfied by Boolean algebra. So first property set, it was dealing with lattice. Second, it was for complemented lattice. Third one, it was for distributive lattice. Then next one for bounded lattice. And fifth part, it was for partially ordered relation. Okay, so there are 5 different categories of Boolean algebra properties. We have seen this part last time. Now today we are going to see the next point, here they have given one example of Boolean algebra. Okay, so let b is equals to 0 comma 1. So b, this is a set and it is containing elements 0 and 1. Then operations star, XOR, complement on b are given by following tables. So three tables are given here. First operation is star operation, second one is XOR operation, and third one is complement operation. Then this b star XOR complement 0 comma 1 is called as Boolean algebra. Okay, so we have seen Boolean algebra is defined by notation b star XOR complement 0 comma 1. So b, this is the set and b stands for Boolean algebra. Then star XOR complement, these are the three operations, those are performed on b. 0 and 1, these are bounds of that set or bounds of that Boolean algebra. Now we have to check how we have defined these three operations. So first operation is star operation. So 0 star 0. So what will be the value? Final value for this star operation? Star
Zero.
means what? Yes, 0. So again 0 star 1, that is greatest lower bound of 0 and 1. So answer for this, just you have to imagine 0 is the lowest element and 1 is the greatest element. Okay, so star operation means what? All the time we are checking for the greatest lower bound, that is least element. So 0 star 0, it is 0. 0 star 1,
Zero.
again 0. 1 star 0, 0. And 1
Zero.
star, yes, 1 star 1, it is 1, because we have already seen this lattice satisfies idempotent property. Means what? 0 star 0, answer is 0. 1 star 1, answer is 1. 1 XOR 1, answer is 1. 0 XOR 0, answer is 0. This is idempotent property. Next operation is XOR operation. So XOR means what? We are going to check least upper bound. So 0 XOR 0, answer is 0, because this satisfies idempotent property. Then 0 XOR 1, what is the answer for this? 1, because here 0 is the least element and 1 is the greatest element. So XOR operation means what? We are going to check for least upper bound, that is greatest element, and that element is 1 here. Then 1 XOR 0. So again answer for this is 1, and 1 XOR 1, again this is idempotent, so answer is 1. Now last operation is for complement. So we have already seen complement for 0, it is 1, complement for 1, it is 0. Now suppose there is one element x, so its complement will be denoted by x complement. So if value of x is 0, then complement is 1. If value for x is 1, then its complement will be 0. So likewise, it is closed under star, XOR and complement operation. That's why B is a Boolean algebra. So likewise, you can give example of Boolean algebra. If whatever set you have taken, here we have taken that set as 0 comma 1. So if you perform star, XOR complement operation on these two elements, all the time it will give you answer as either 0 or 1. Means what? This is closed under operations star, XOR and complement. That's why this set is called as Boolean algebra. Have we understood this example?
Yes, Yes, ma'am.
Okay, good. Now, let us see next example. Let S be a non-empty set and P of S be its power set. The set algebra PS, that is power set of S, intersection, union, negation, phi and S is a Boolean algebra in which complement of any of subset A is subset of S, that is denoted by negation of A, that is S minus A, that is relative complement of set A. If S has n elements, then P of S has 2 raised to n elements. Then diagram of Boolean algebra P of S intersection union when S has elements 1, 2, 3 are shown in figure. So here they have given one set S, that is non-empty set. P of S is power set of S. Again, there are three different operations are defined on power set of S, that is intersection, union and negation. Negation means what? Complement. Okay. Then negation of A. This is equals to S minus A. The elements those are present in S but not in A, that is denoted by negation of A. Now here they have given set S is containing 1, 2, 3 elements. Then we have to draw the diagrams for Boolean algebra for power set of S. So first of all tell me, if set S is containing just one element, then how many elements will be there in power set of S? We have already seen this formula.
2.
Yes, that is 2 raised to 1, that is equals to 2. So first diagram represents two elements and this is for power set of 1. So this Boolean algebra is for power set of 1. Now next one is 2. So if your set is containing two elements, then its power set will contain 2 raised to 2, that is equals to 4 elements. And that Boolean algebra is represented by second diagram. And third one, if your set is containing 3 elements, then power set of that set will contain 2 raised to 3, that is equals to 8 elements. And that is represented by last diagram. So likewise, we can give examples for Boolean algebra. So for this, they may ask you question like give examples of Boolean algebra or give example of Boolean algebra for 4 marks. At that time, you have to give any one of these examples. Have you understood this example? Here just they have shown how to represent any Boolean algebra based on number of elements in that particular set. Have you understood?
Yes, ma'am.
Okay. Now, next part is very interesting, that is subalgebra, direct product and homomorphism. So again we have to represent this with respect to Boolean algebra. Here before we have seen this for monoid, then semi-group monoid, then lattice group. Now we have to see this is for Boolean algebra. So first definition is for sub-Boolean algebra. So let B star XOR complement 0, 1 be a Boolean algebra and S is subset of B. If S contains elements 0 and 1 and it is closed under operations star XOR complement, then S star XOR complement 0, 1 is called as sub-Boolean algebra of B. Okay. So likewise we have defined set subset. Same here we have to define for sub-Boolean algebra. So So if Boolean algebra B star XOR complement 0, 1 is given, so here star XOR and complement, these are three operations defined on B. Again 0 and 1, these are bounds of B. Then if there is any another set like S, if S is subset of B, and if S is closed under three operations like star, XOR and complement, and if S is containing 0 and 1, then S star XOR complement 0, 1, this is called as sub-Boolean algebra of given algebra. Have we understood this definition? First condition we have to
Repeat,
check.
ma'am.
Yes. So first condition we have to check S must be subset of B. Okay. This is the first condition. Second one, it should closed under operations star, XOR and complement because these are operations of given Boolean algebra. And third one, it should include 0 and 1 because 0 and 1, these are bounds of Boolean algebra. That's why S must include 0 and 1. Then only S star XOR complement 0, 1 is called as sub-Boolean algebra of given algebra B. Understood now? जसे आपण बाकीच्या डेफिनेशन बघितलेत, सब लॅटिस असेल किंवा सब मोनोइड असेल, सब ग्रुप असेल और सब सेमी ग्रुप असेल. So likewise here also we have defined sub Boolean algebra, and for that first Boolean algebra how we have defined B star XOR complement 0, 1. So why we have given all these elements? Because B, this is set, and on this set we have defined three operations star, XOR, complement. Okay, means what? That set B is closed under these three operations. Now 0 and 1, these are bounds of given lattice. That's why 0 and 1, this is part of B. Bounds we have seen already. Bounds means what? Least element and greatest element. Now we have to check whether S is sub-Boolean algebra of B or not. So S can be a sub-Boolean algebra of B if and only if first condition S must be subset of B. That we have given here. S is subset of B. Now second one, S must be closed under operations star, XOR and complement. This is second necessary condition. And third one, it should include elements like 0, 1. Then only we can say that S star XOR 0, 1, this is sub-Boolean algebra of given algebra B. Are you getting now? Hello?
Yes, ma'am.
Okay. Now, they have given some note how to check whether given set is subalgebra or not. So, it is not necessary to check for closure with respect to all three operations star, XOR and complement, nor it is necessary to check whether 0 and 1 are in S. Only closure with respect to set of operations star, complement or XOR complement is enough to guarantee the set S is subalgebra. Okay, so this is very important note what they have said. So it is not necessary to check closure with respect to all three operations. So what are these three operations? Star, XOR, complement. So all the time it is not required to check closure with respect to all these three operations. So neither it is necessary to check whether 0 and 1 are present in S. So in order to check whether given set is subalgebra, you have to just remember two conditions. Your set must be closed under star and complement operation, or it must be closed under XOR and complement operation. So these two sets are very important in order to check whether given set is sub-Boolean algebra or not. Okay. So based on this, we are going to solve the example. So here they have given just one case. If for any A and B belongs to B, A XOR B, this is equals to A's complement star B's complement whole bracket complement. So these two formulas are equivalent, or these two statements are equivalent. How? Can anybody explain why these two statements are equivalent? Yes, just think on it and tell me how we have written these two statements as equivalent. Okay, so before that, just tell me what will be the complement for A XOR B, whole bracket complement. So what is the answer for this complement? Just tell me what is complement of A? How we can represent it? Yes, anybody? Very simple question is there. How we can represent complement of A? What is complement of star operation? Yes, we have seen this in the part of lattice only. What is complemented lattice? Okay, see here. If we want to take complement of A XOR B, for this brackets complement, we can write its complement as A's complement star B's complement. Okay, so here we have taken complement of that bracket. But if you take complement only, then it will change its meaning. That's why in order to nullify effect of complement, it is required to take double complement. Likewise, in the first chapter only we have seen negation of negation P. This is equivalent to P because negation gets cancelled. Now here for this A XOR B, if you take complement one time, it will give you A's complement star B's complement. Now, in order to nullify its complements effect, it is required to take another complement, and that complement is written here as A's complement star B's complement whole bracket complement. Means what? Again here complement will get cancelled and its answer will be same as A XOR B. That's why A XOR B, this is equivalent to A's complement star B's complement whole bracket complement. Have you understood how these statements are equivalent? Hello? Are you there? Yes, what happened? Are you getting this or not? जोपर्यंत तुमच्याकडून काही रिस्पॉन्स येत नाही तोपर्यंत मी कंटिन्यू करणार नाही आहे. तुम्हाला समजलं नसेल तसं सांगा, मी परत एक्सप्लेन करते.
Repeat, ma'am.
Okay. So here we have to check how these two statements are equivalent. So first one is given as A XOR B. Okay. Now just imagine we have to take its complement. So A XOR B whole brackets complement. So again A's complement is, how we can represent A dash, that is A's complement. Now complement of this XOR operation, this is star operation, and B's complement means what? B dash. So our answer will be A dash star B dash. So this is answer we got if you take complements only one time. But if you take this complement only once, then it will change meaning of original statement. So likewise P, this is not equivalent to negation of P. Okay. P and negation P हे equivalent नाही आहेत. But if you want to take complement or negation, in order to take, you have to take that complement twice. Like P, this is equivalent to negation of negation P, because again here negation will get cancelled and answer will be P is equals to P. So likewise here you can't take complements only once. That's why it is request to take that complement twice. Then only those two statements will be equivalent. Now here in this case A XOR B, if you take complement only one time, you will get answer as A complement star B complement. Now we have to nullify effect of complement. That's why again we need to take complement, and that complement is given as whole bracket complement here. A complement star B complement whole bracket complement. Now these two statements are equivalent because we have taken complement twice. That's why these two statements are equivalent. Are you getting now?
Yes, ma'am.
Okay. So likewise for next two statements you have to think how we have written there. One is equals to A star A's complement whole bracket complement, and 0 is equals to A star A's complement. Take time of 5 minutes and tell me how these two statements are equivalent. Okay. Just tell me what is the answer for A star A's complement whole bracket complement. What is this equivalent form? Apply this complement over this bracket and tell me what is the equivalent formula.
A complement XOR A.
Is A complement XOR A. So again, what is the value for A XOR A's complement? Means what? Least upper bound of A and A XOR. So XOR operation means what? Here we have defined 0 and 1. These are the bounds of lattice. So XOR operation means what? Greatest element. So greatest element for this Boolean algebra is 1. That's why this A star A's complement bracket complement this is equivalent to 1. समजलं का? 1 कसं आलंय? Because once you apply that complement over that bracket, you will get A's complement XOR A. So again, XOR operation means what? Greatest element. And here that greatest element is 1. That's why this is equivalent to 1. Have we understood?
Yes, ma'am.
Okay. Now check for next one. A star A's complement. So again here we have defined star operation between A and A's complement. So star operation deals with least element. And here we have defined least element is 0. That's why A star A's complement this is equals to 0. Okay. So here they have given one example of Boolean algebra. Check. Let S is equals to set ABC and power set of A that is defined as phi set A, set B, set C, set A comma B, set A comma C, set B comma C and set A, B, C. Okay, so this is the power set of S. Then the Hasse diagram of lattice power set of S union intersection is as shown in figure. So here they have given one example of lattice which is closed under operations union and intersection. So set S is containing 3 elements. That's why its power set will contain 2 raised to 3 that is equals to 8 elements. And those 8 elements we have defined here. So how we can define lattice? First element is phi, then next one is set A, then set B and then set C. Now here A and B these are getting connected into set A comma B. B and C these are getting connected into set B comma C. And A and C these are connected into set A comma C. Now set AB, set BC and set AC. These 3 sets are connected into set S and that is equals to set ABC. Now this set is closed under operations union and intersection. Again we can check here. This is a complemented distributive lattice and here least element is phi and greatest element is S. That's why this lattice is called as Boolean algebra because we have seen Boolean algebra is distributive, complemented and bounded lattice. So here this lattice satisfies distributive property. This is a complemented lattice because here complement exists for each and every element. Again this lattice is containing bounds. So here least bound is phi and greatest bound is set S. That's why this lattice is called as Boolean algebra. So likewise, you can give example of Boolean algebra. Have you understood this part? Hello? Shall I repeat this?
Yes, ma'am.
Okay. So see here, question is given as give an example of Boolean algebra. They have asked you to explain any one of the example of Boolean algebras. Now, last time we have seen in this lecture only, we have defined two Boolean algebras. So likewise, again we have to define here one more algebra. So here for that purpose we have taken one set S, and that is containing three elements as A, B, C. Now we have taken power set of S. As S is containing three elements, power set of S will contain 2 raised to 3, that is equals to 8 elements. Now what are those 8 elements? In this set theory only we have seen first element of every power set is 5. That's why first element of power set of S, it is 5. Second element is set A, then set B, then set C, set A comma B, set A comma C, set B comma C, and set A B C. So here there are total 8 elements in power set of S. Now first of all we have to draw lattice for this power set of S, and which is closed under operations union and intersection. So why we have called this one as this is closed under union and intersection? Because if you take union of A and C, so you will get answer as set A comma C. Now check here. If you take union of A and C, you will get answer as set A comma C, and that is already included here in this diagram. Again, if you take intersection of set A comma B and set B comma C, then intersection means what? Common element. So for these two sets A, B and B, C, set B is common. So that element is also included here in this diagram. That's why we can say that this lattice is closed under operation union and intersection. Now, if you check, this is a complemented lattice. Also, this is satisfies distributive property. And again, here exists least element and greatest element. So here least element is 5 and greatest element is set S. So we can say that this lattice is complemented, distributive and bounded. That's why this lattice is called as Boolean algebra, because in the definition of Boolean algebra itself we have taken if Boolean algebra is complemented, distributive, bounded lattice, and here this lattice is satisfying all these three properties. That's why this is an example of Boolean algebra. Have you understood now? बुलियन अल्जेब्रा का म्हटले कळालं का? येस, समजले का की डाऊट आहे अजून काही? हॅलो,
Yes, ma'am. कळालं.
okay. Okay, so today we are going to stop here. Next lecture we have to see what are the examples of sub Boolean algebra. and how to recognize whether given algebra is sub-Boolean algebra or not. Before that, just give me present T. Roll number 1,
Yes, ma'am.
2,
Yes, ma'am.
3,
Yes, ma'am.
4,
Yes, ma'am.
5. Roll number 5, 6, 7, 8, 9,
Yes, ma'am.
10, 11,
Yes, ma'am.
12,
Present, ma'am.
13, 14,
Yes, ma'am.
15, 16, 17, 18,
Yes, ma'am.
19, 20,
Present, ma'am.
21, 22,
Present, ma'am.
23, 24,
Yes, ma'am.
25,
Yes, ma'am.
26, 27,
Present, ma'am.
28, 29, 30,
Present, ma'am.
31,
Present, ma'am.
32,
Present, ma'am.
33,
Present, ma'am.
34, 35,
Present, ma'am.
36,
Present, ma'am.
37,
Present.
38,
Present, ma'am.
39,
Yes, ma'am.
40,
Present, ma'am.
41, 42, 43,
Present, ma'am.
44, 45,
Yes, ma'am.
46, 47,
Yes, ma'am.
48, 49,
Yes, ma'am.
50, 51,
Present, ma'am.
52, 53, 54, 55. Yes, 54 is present. Okay. 55, 56, 57,
Yes, ma'am.
okay, 58, 59,
59 present.
60, 61,
Yes, ma'am.
okay, 62,
Present, ma'am.
63,
Present, ma'am.
64, 65, 66, 67,
Yes, ma'am.
68, 69, 70. Okay. So check for today's absent numbers. Roll number 5, 6, 7, 8, 13, 15, 16, 19, 21, 23, 26, 28, 41, 44, 46, 48, 50, 52, 53, 55, 58, 65, 66, 69, and 70. Any corrections? Okay, so today we are going to stop here. Thank you.
Ma'am.